Communicate never just about information, but also emotions. So in this session, we are going to have 4 papers talking about communicating emotions through different modalities and evaluating environment emotions through different technologies. And the first paper we are having is Towards Multimodal Affective Feedback, Interaction between Visual and Haptic Modalities. The authors are Akshita, Harini, Bipin from IAPS India, and Eunhwa Li, Yudong from Samsung Electronics.
Hello everybody. I'm Harini. I'm a graduate student at the Cognitive Science Lab in IIIT Hyderabad. My co-author Akshita is here. This work was done in collaboration with Samsung Electronics Korea, and this work is about how we could generate multimodal affective feedback. Let us consider a newsreader application. So this is going to be an emotionally intelligent newsreader application. So let us say that the news has some very disturbing or shocking pictures. So I want my application to generate a haptic feedback so that it calms my user down. Now, the question is this even possible? Can I generate such a haptic feedback? And if it is possible, how should I generate the haptic feedback? Which brings us to a research question. How do emotional cues present in visual and haptic modalities interact? And how can this knowledge be used to generate and create multimodal affective interfaces? Now, research in cognitive science and psychology has long established that multimodal integration is not a straightforward process. When human beings get conflicting information from different sensory modalities, either one of the sensory cues could override the cue from the other sensory domain, or you could get a completely novel percept. There are many classic examples in literature like the rubber hand illusion, the ventriloquist effect, and the parchment skin illusion, for any combination of modalities you could think of. Coming to HCI, research on multimodal feedback is getting more and more important these days, because multimodal feedback gives us a very immersive and natural user experience, and with the advent of small form factor mobile devices, unimodal visual interaction is no longer sufficient. And there is a wealth of research on how effectively you could provide information to users across modalities. But comparatively, the amount of research on multimodal affective feedback is very less. The only closest work what we could find similar to the research what we were doing was the one by Bonnet, where they found that using haptic feedback actually improves the recognition of facial emotions of a virtual character. So this motivated us to ask the general question of how do we actually integrate multimodal affective information. For example, if I gave you a happy emotional cue in your visual modality and a sad emotional cue in the haptic modality, what would you feel? Would you feel happy? Would you feel sad? Or is it going to be a completely new emotion? So how did we go about doing this? First, we needed visual data set with affective ratings. Then we designed a haptic data set with affective ratings. Finally, we studied like how affective information presented in visual and haptic modalities interact. And finally, we explored this interaction in terms of haptic features. I will explain this bit in a bit later, so that we could design multimodal interfaces. So before I actually go into the details of my experiment, a little bit of background on the concepts of valence and arousal. So research in emotions, especially research in emotions from psychology, has long established that asking users to label an emotion is not very reliable. For instance, if I ask my user show my user an image and ask them, okay, is this sad, is this happy? So those kind of ratings are not considered reliable. So people use models of emotion. The most famous of them is the circumplex model of emotion, in which emotion is a point in two-dimensional space. These two dimensions being arousal and valence. Arousal decides how exciting or calming a particular emotion is, and valence decides how pleasant or unpleasant an emotion is. So for example, being relaxed would mean like it's high valence but low arousal, whereas being bored would be low valence and low arousal. So we use the circumplex model of affect in our work. So the next step was to choose an affective visual data set. Now thankfully there already exists an extremely well-cited visual data set. This is called the International Affective Picture System. This has 1192 images with valence and arousal ratings. But our experiments were conducted with Indian participants, and this data set has never been tried with that target group. So we first conducted a pilot to test the validity of IAPS with Indian participants. So what we did was we chose a representative sample of 120 images from the original data set. We gave them to 8 Indian participants, and we asked them to rate those images on valence and arousal. Now we took these ratings from the participants and compared it with the original IAPS ratings. What we found was that there was no significant difference in the ratings we got from the Indian participants and from the IAPS dataset, which means that the ratings from the original dataset can be used with Indian participants. The next step is to create a haptic dataset, an affective haptic dataset. But unfortunately, we did not have such a dataset readily available, which meant we had to create one. So before I go into the details of the haptic dataset, we used in our experiments the Vivid Touch haptic actuator, the one you see on the right. So this is a sufficiently broadband actuator with a 0 to 200 hertz bandwidth. So coming back to the creation of the haptic dataset, we first had to choose the dimensions along which we would vary the haptic stimuli. So we chose intensity, frequency, waveform, and rhythm. This choice was primarily dictated by work in existing literature on haptics. The details are in the paper, but I won't go into them now. So what we did was we sampled each dimension based on the limits of human perception and the limitations of the haptic device. For example, when we chose frequency values, we could not go beyond 200 hertz because the limit of our haptic actuator itself was 200 hertz. Then, for example, in intensity, we could not go beyond 55 dB because that is the point at which for human skin, the haptic vibration starts becoming painful. So 55 dB is the limit of human perception. So we couldn't choose a value more than that. So based on this, we created a set of haptic stimuli. So we ended up with 390 stimuli. Now, this was a large data set. So our next step was to prune this data set. Our goal was to make sure that all the haptic stimuli in the data set was perceptually discriminable. So we conducted a series of discrimination experiments with our participants. Basically what we did was we played 2 haptic stimuli, one after the other, and we asked them if they could discriminate between those 2 stimuli. If they were able to discriminate, fine. If they were not able to discriminate, then we tweaked the parameter values. So we increased the spacing. So like this, we conducted a set of iterative experiments, at the end of which we came to a data set of 180 stimuli. Again, the details of all the experiments are available in the paper. What you see on the right is the final data set we had. So we had 10 rhythm levels. The rhythms are shown there. This rhythm set was actually inspired by the work of McLean. So the gray boxes are the on duration. The white is the off duration. So the rhythm is an on-off pattern. We chose 3 waveforms: sine, sawtooth, pulse, frequencies, 3 frequencies, 55 hertz, 110 hertz, and 165 hertz, and 2 intensity levels. So the next step is, now that I have my haptic data sets, I need the affective ratings for this haptic data set. So we conducted actually a pilot in which we gave the haptic stimuli to participants and asked them to rate it on a 9-point scale. Now, participants found this task very difficult, and the reliability of the ratings were also not accurate. Basically, because they felt that the haptic stimuli was too abstract for them to rate on a 9-point scale. So what we did was, we decided not to get a 9-point rating, but we went back to the circumplex model of effect and created a grouping scheme like this. So what participant had to do was to play each haptic stimuli and group it into one of these 9 groups. So which would give us 3 ratings for arousal, basically low, neutral, and high, and 3 ratings for valence, low, neutral, and high. So the result of this rating process was this. So intensity had a very major role on how participants perceived the effect. Low intensity stimuli was perceived as having low arousal, and low intensity stimuli was perceived as having high valence. So basically this was a calming and pleasant effect. Frequency had no effect on arousal, but it had an effect of valence, that low frequency images were perceived as having low valence. When it came to waveform, sine and sawtooth were perceived as more calming and more pleasant compared to pulse, and rhythm had no significant effect on the haptic ratings. So now I have my affective visual data set. I have my affective haptic data set. So the next question to ask is, how do the affective cues presented in visual and haptic modalities interact? So what we did was, we combined the visual and haptic stimuli under 2 conditions. So in the supportive condition, my visual and haptic, both of them convey to the participant the same emotional cue. If the visual stimuli is low valence, my haptic stimuli is also low valence. In the conflicting condition, the emotional cues in visual and haptic stimuli, as the name suggests, are conflicting. So if there is a low valence visual stimuli, the corresponding haptic stimuli is high valence. So we pair the visual and haptic stimuli under all these 8 conditions. So there were like 40 stimuli in all, and each participant rated the visual haptic stimuli on a 9-point scale. So these are the results of the experiment. The ratings have been converted to a 3-point scale so that you can compare the visual and visual haptic on the same range. Values close to 1 are low, and values close to 2.52 are high. So what you can see is, when both the visual valence and the haptic valence were low, there was no significant difference between the visual haptic valence and either of visual or haptic valence. The same is true when both visual and haptic valence were high. But when the visual and haptic valence were conflicting, what we found was that the visual haptic valence was very close to visual valence. Irrespective of whether the haptic was low or high, there was no significant difference between the visual and visual haptic valence. In arousal, in the supportive condition, what we found was the visual haptic arousal was always higher than the visual arousal. In the conflicting condition, we found the same effect, that the visual haptic arousal was higher than the visual arousal. But the most interesting result is on the right-hand image, that even when the arousal of the haptic stimuli itself is low, the visual haptic arousal was still higher than the visual arousal. So summarizing these results, what we found was, in the supporting and conflicting valence conditions, the visual haptic valence closely follows visual valence. So it is the visual component of the visual haptic stimuli that decides the valence. Again, both in supporting arousal and conflicting arousal cases, just the mere presence of a haptic signal, irrespective of whether the arousal of the haptic signal was low or high, we always ended up with a visual haptic arousal, visual haptic stimuli whose arousal was much higher than the visual arousal. So this kind of gives an initial picture of what happens when emotional cues presented in visual and haptic modalities interact. So the next question to ask is, so how do I use this knowledge to probably design an interface or design the haptic feedback? So what we did was we first explored the second condition, the visual haptic arousal being greater than visual arousal. So what we first investigated was how do the features of the haptic stimuli contribute to this this difference in arousal. So how do the features of the haptic stimuli affect the arousal? So we took our initial affective haptic data set. So initially in my results on haptics, I said rhythms were not a significant parameter affecting the haptic ratings. So what we did was we just chose 6 out of the original 10 rhythms, because by this time we had gained a reputation of running very long experiments. So we had to bring participants into our lab. So we cut down we chose 6 rhythms out of 10 rhythms. We divided them into 2 groups based on intensity. So L, which is low haptics, low intensity, contained the 20 dB stimuli. Hap H, which is haptics high intensity, contained the 35 dB stimuli. So we had 54 stimuli in each. Now we paired this with the visual images from IAPS. So we chose 3 categories of images with low arousal, medium arousal, and high arousal. The valence was maintained at neutral. And each set of images, 54 images, was rated by one group of participants. So we had 24 participants in all. So from this group, we obtained the ratings for visual stimuli, the haptic stimuli, and the visual haptic stimuli. So the results were arousal difference. So what you see on the left here is actually the arousal difference. So this is the visual haptic arousal minus the visual arousal. So which feature of the haptic contributes highest to this arousal difference is the question here. So what we found was intensity. The arousal difference at 35 dB was significantly higher than arousal difference at 20 dB. There was a significant interaction between intensity and frequency. So at low intensity, low frequency, haptic stimuli resulted in higher increase in arousal. We did not find any significant effect of waveform or rhythm. So finally, these are the guidelines summarizing. So what we found was that Valence ratings of the visual haptic stimuli is dominated by the visual component. The presence of haptic, the mere presence of haptic increases the arousal of the visual stimuli. Intensity and frequency of haptic stimuli play a significant role in increasing the arousal. Waveform and rhythm do not. So where do we go from here? Now I asked only one question, that how does haptic affect arousal? So to complete this work, I also need to explain how visual stimuli would affect the valence of the visual haptic stimuli. This is something we are working on, but the tricky thing has been to characterize the visual stimuli the same way we characterize the haptic stimuli. Again, the next thing is the results what we presented were from the VBTouch haptic actuator. So we are planning on repeating the experiments with multiple haptic devices to see if the results hold. And we are, as a natural extension, interested in what happens when affective information presented in audio and haptic cues interact. So this work was funded by Samsung Global Research Program, Outreach Program. We are thankful, and we thank Google and Microsoft for the travel support to getting us here to Seoul. And with that, I'd open the floor for questions. Thank you.
Yeah, please announce your name and affiliation.
Hi, Gershon Dublan, MIT Media Lab.
Hi.
I have a question that might be off base, so if you don't have an answer, that's totally fine. I'm just curious. There have been some kind of questions recently raised about sensory substitution devices and their relation to affect. In particular, I guess questions about whether it's possible that say visual to haptic sensory substitution device would produce an affective response in a wearer, and generally the answer has been the outlook hasn't been too good, and there haven't been many emotional responses to those
Right.
kinds of prosthetics. So I was wondering if you could comment on that.
Yeah, I mean, like, I think sensory substitution was how haptics research first started the interest, if you look at the early work. But I don't think our aim was to do sensory substitution. That's a very difficult thing, I agree to you. But more like how these two modalities interact rather than, substitute one another.
Do you think that there may be some sort of way to get at that question in what you've uncovered about the relationship between, at least the dominance between either of those sensory modalities? I mean, I guess you discovered the dominance of the visual. Is there something to be gained?
Yeah, I think that's a possibility to think about it. Thank you.
Thanks.
Yeah.
Hi, Steve Rees from University of Glasgow. I was kind of surprised that you didn't find any effect for rhythm. So you can imagine a very slow and calm thing, very fast, staccato, asynchronous.
Yeah.
I would have expected you would have found some kind of arousal effect.
Agreed, but I think that also has, because rhythm is, I mean, I could choose an infinite set of rhythms. We restricted to those 10 rhythms what we chose. So I think, to be honest, I should say, like, when I said rhythm did not have an effect, those 10 rhythms did not have an effect. So we should explore that parameter further.